Have you ever faced the challenge of retrieving information from data structures where items are nested within one another, like an organizational chart or a product category tree? It can feel like navigating a complex maze, trying to understand relationships and ancestry. To query hierarchical data efficiently, the key lies in selecting an appropriate data modeling strategy and leveraging specific database features. The most common approaches include using adjacency lists with recursive common table expressions, implementing path enumeration, employing nested sets, or utilizing closure tables. Each method offers distinct advantages depending on the type of queries you need to perform most frequently. The inherent difficulty with hierarchical data stems from its recursive nature. Traditional relational queries are designed for fixed-depth joins, struggling when the depth of the hierarchy is unknown or varies. This necessitates specialized techniques that can traverse arbitrary levels of parent-child relationships without resorting to an unwieldy number of self-joins, which can quickly become a performance bottleneck. For the adjacency list model, where each record points to its direct parent, efficient querying often involves recursive common table expressions, or CTE for instance. To find all descendants of a specific node, you would define an anchor member identifying the starting node and a recursive member that joins the CTE to the table itself to find children of the previously found nodes. This approach gracefully handles hierarchies of any depth, providing a clear and standard way to walk up or down the tree. Another powerful strategy is path enumeration, also known as the materialized path model. Here, you store the full path from the root to each node as a string in a dedicated column. For example, a path might look like a /b/c, queries for subtrees or all ancestors become incredibly simple and efficient, often using basic string matching operations like a like clause or a starts with predicate, especially when this path column is properly indexed. This significantly reduces the computational overhead for common tree traversal patterns. The nested set model represents each node with a left and right boundary value, effectively creating a numbered range. A node's descendants are all nodes whose left and right values fall within its own range. This model excels at finding all descendants of a node or checking if one node is a descendant of another with just a few simple comparisons, making subtree retrieval extremely fast. However, inserting or deleting nodes can be more complex, often requiring re-indexing large parts of the tree. Finally, the closure table model involves creating a separate table that stores every possible ancestor-descendant relationship. This means for a hierarchy with 100 nodes, this table might contain thousands of entries. While it requires more storage and has higher write overhead due to inserting multiple rows for each new node, querying for any ancestor or descendant of a given node becomes a single, highly optimized join operation against the closure table, making read operations exceptionally fast. Understanding the trade-offs between these modeling techniques is vital. Many modern relational database systems, such as PostgreSQL, MySQL, and SQL Server, offer robust native support for recursive common table expressions, which makes implementing the adjacency list model quite powerful and often the first choice due to its simplicity in data manipulation. The judicious application of indexing on key columns, whether it is the parent ID in an adjacency list, the path string in path enumeration, or the left and right values in nested sets, is paramount to achieving optimal query performance. By carefully choosing the right hierarchical data model and leveraging specialized query techniques like recursive common table expressions or efficient path matching, you can transform the challenge of navigating complex nested data into a streamlined and highly performant operation. This ensures that your applications can quickly retrieve and analyze intricate relationships, providing robust and scalable solutions for deeply structured information.
If this helps you code smarter, like, subscribe, and stay tuned for more.